you are given a capacitor and you don't know its power, you don't know its capacitance, and you are actually asked to tell us what is the capacitance of that capacitor, and you are given all the requirements. You are given the reed switch circuit arrangement. How do you determine the capacitance of that capacitor? Remember, we are saying that capacitance is the ratio of magnitude of charge to the potential difference. You can refer to the previous lesson. So therefore, when I need to get this capacitor, I put it in this arrangement as shown. And by the way, this arrangement is very important for the capacitors. Almost all the experiments we shall do, we shall be using this same arrangement when you are using the reed switch circuit. So you just have to know, you have to put your capacitor here in power with the PD supply, and then you have an ammeter there, then the reed switch circuit there, the voltmeter there, and the way you can see, we have this reed switch. This K is a reed switch which will be touching at X and Y respectively. So what do? You just have the setup of the arrangement like I have explained. Then what do? You activate this reed switch circuit at a suitable frequency. Let's say you activate it at a suitable frequency F. What happens? When you activate it at a suitable frequency F, which is very high, of course, this switch K will touch X and Y respectively at very high speed, thereby completing the circuit, and the current will pass through this one. Because when it touches at X, it charges this capacitor. When it touches at Y, it discharges the capacitor. But at each of the points, as it touches here, the current will be flowing. As it touches here, the current will be flowing. Okay? As it flows, you shall record the current flow I. It touches at X and Y. It charges and discharges the capacitor. You record I. You have recorded, of course, the voltage V that is given by the PD supply. You can see this, the potential divider. It can move along to either increase or reduce the PD. Meaning that for every value of potential difference, you will record the current I. You are going to repeat this experiment by varying the PDV by either moving this one down or upwards. And when you do that one, you also get the current I. And after doing that one, you are going to draw a graph of I against V. I against V. And actually when you draw that graph very well, it will be a straight line graph, and it will actually pass through the origin. You know how to get the gradient of this. So you calculate the gradient, maybe you call it M, and the capacitance of this capacitor will be equal to M out of this suitable frequency at which your reed switch circuit was activated. By doing so, you have determined the capacitance of this capacitor that has been given to you. Therefore, you can go ahead and use it for any activity as you may want, as you may wish. How does it come to M over F? That's what I want to explain. How does it come to M out of F? This is very simple. From the previous lesson, we said that current I is the rate of flow of charge, which becomes 2F because 1 over T is F. But we said that charge is CV, so I equals CVF, which I can say that I equals CF then V. We are plotting I against V, meaning this becomes our Y, this becomes our X. And from the general equation of a straight line, that Y is always equals mx plus c. You realize that the coefficient of x is the gradient. So this is the gradient, okay? And our constant is 0. Our y-intercept is 0. That's why we are saying it must pass through the origin. It does not pass here because it would give us a c. We are saying our c is what? Our c is 0. Therefore, m equals Cf, but we want the capacitance of the capacitor. Therefore, by dividing by f both sides, we shall have that the capacitance will be the gradient out of the frequency that this reed switch circuit was activated. This is simply the way it can be got. So what did I say? I said the reed switch circuit K is activated at a suitable frequency F. That is point number 1. Somebody would wish to write notes, and therefore you got the second line. You may call it a paragraph. It's up to you, either a new line or a paragraph. In physics, we accept both. The capacitor C, that's the new line, is continuously charged and discharged by K, making contacts at X and Y respectively. Is charged by K making contacts at X and Y respectively. Then another new line. The ammeter reading I is measured and recorded in amperes. And the voltmeter reading V also measured and recorded in, you say it. Voltage is measured in, thank you for saying volts, yeah, in volts. We are almost done with the experiment. Okay, another new line. The experiment is repeated by varying the PDV across the capacitor plates, and the results got are tabulated. So when you use a different value of V, you obtain a different value of I. The results got are tabulated. A graph of I against V is plotted and is a straight line through the origin. Maybe you can have this sketch there. Just have that simple sketch. This is I against V, and it will be a straight line that will be passing through the origin. You can have it there. And then, of course, we shall calculate its what? This is changing I, this is changing V. By doing so, we shall be able to get the gradient. The gradient of the graph, that's M equals changing I out of changing V, is calculated. And the capacitance of the capacitor C is equal to the gradient out of F. Is equal to the gradient out of F. The gradient, the F, remember we had it here, and we have got that one. So if you want, you can also take note of this, though we always don't require this one in the description of the experiment. But you can also take note of it so that in the future when you are revising, you don't start asking yourself many questions. How does C become M out of F? So by doing so, you have had an experiment to determine the capacitance of that given capacitor. Remember, all understanding will be found at BAC, BAC Science Education Consultants. your teachers are there ready to help you in all your questions. Feel free to contact us and we help you. Everything is available for only and only you, so that the learning may continue taking place. I'm still teacher course, by the way, and we want to determine the capacitance of a charged sphere. Capacitance of a charged sphere. So, a charged sphere, I can maybe represent this one. Of course, the field lines, they spread radially along the radius, as if, and therefore that shows as if the charges are concentrated at the center. So let's say this sphere is charged positively. Want to know if we make a capacitor in form of a sphere, which is 1, how shall we be able to calculate that capacitance? So the charges appear as if they are concentrated at the center. You know this one, you have seen, and then we can say maybe it has a radius r. So the charges are like concentrated at the center. Okay, that's the behavior since they are moving like this one. So it's as if the charge is concentrated there. What's the potential of a charged sphere? Remember in the previous lessons in electrostatics, if you haven't checked there, in electrostatics lessons, study by following all of them. We said that the potential at the surface of the sphere V is equivalent to the charge out of 4 pi epsilon naught r. That is what we say. If this is the magnitude of what? The magnitude of charge. From definition, capacitance is the ratio of the magnitude of charge to the potential difference. Capacitance is the ratio of magnitude of charge to the potential difference. So the charge is this, potential difference is this. So what do you get? When you get this divided by this will be equivalent to charge out of 4 pi. Charge then divided by this, which will be the multiplication of the reciprocal. So this charge will cancel with that, and we shall have capacitance equaling to 4 pi epsilon naught r. So you realize that the bigger the radius, the bigger the capacitance. By the way, we have the reciprocal of this. From the previous lesson, we had that 1 out of 4 pi epsilon naught is 9 exponent 9. So since we have it here, we take its reciprocal. So we shall have our capacitance equivalent to, now this the reciprocal of this will be 1 over that. Then the r will be on top, and we shall have it like that. So this is the capacitance. This is the capacitance of a charged sphere. That's the capacitance. So if we have a capacitor which is made in that form, then that would be the expression for the capacitance. And we are going to use such expressions in some other subsequent lessons while solving some problems in order to get the capacitances and etc and etc. I'm still the same teacher course of back science education consultants. Please, you need always be there at that, and don't forget to subscribe to our channel. Don't forget to invite your friends. Thank you for doing that one. May God bless you. What if here we have two spheres which have the same center? What would be the capacitance? I guess you have already taken that. You can pause the video and handle, and then we proceed. Yes. Now this was one. Now we want to see if these spheres were two. Of course, one with a smaller radius than the other. They are concentric. They have the same center. So you can say capacitance of concentric spheres. Yes. So let's say that one is in this one. They are sharing the same center. This one has a radius R1, and maybe this one has a radius R2. We want to have this one asked so that it is the outer part is at zero potential. And so if this one has a charge, a positive charge to the outer part of the inner sphere, it will induce a negative charge on the inner part of the outer sphere. Okay? It will induce that same, which will be now negative charge. Yes, it will induce it there. And therefore, what is the potential difference of the arrangement? It will be the potential difference due to the inner sphere minus, or I can say it will be the electric potential due to the inner sphere. The V of the arrangement will be the potential due to inner sphere minus potential due to outer sphere. That will be the potential of the whole arrangement. But the potential of the outer sphere is zero since it is Earth. Therefore, this will be equal to the potential due to the inner sphere, maybe, which we can call V1. Okay? But still that potential of the whole arrangement, you can see it is depending on now the potential here and the potential there. Okay? Where the potential here will be positive charge out of 4 pi epsilon naught R1. And then the potential there, when we add, will be, of course, the charge is negative 4 pi epsilon naught, then R2. Therefore, this will be equal to, I can factorize out charge out of 4 pi epsilon naught. Here I remain with plus 1 out of R1, then minus 1 out of R2. And then I can do the LCM. This is charge out of 4 pi epsilon naught. This will be R1, R2. This divided by this will be R2, R2 times this will be R2. This divided by this will be R1, R1 times 1 will be minus R1. That is the V. That is the potential difference. But we want the capacitance, which is 2 out of V, which will be the 2 out of this. So when I get the charge, then I divide by the charge out of 4 pi epsilon naught r. I have this out of this epsilon naught, then into r2 minus r1 out of r1 r2. So of course when I divide by this, I will be multiplying by the reciprocal. The charge will cancel and I will have, you can see that this is down, so I have 4 pi epsilon naught r1 r2 out of r2 minus r1, where you can also handle this and you say that is 1 out of 9 exponent 9, so the whole thing can become r1 r2 out of 9 exponent 9 into r2 minus r1. That would be, maybe I can have it here so that it becomes more clear. r1 r2 out of 9 exponent 9 into r2 minus r1. That would be our capacitance of two concentric spheres, one of a smaller radius r1, another one of a bigger radius r2. That would be the capacitance. That's how we shall be able to calculate that capacitance. So what did I say? I said that suppose two hollow concentric spheres are arranged as shown in the figure, with the outer sphere Earth on its outer surface and the inside sphere with a charge of positive Q on its surface. Negative charges of magnitude 2 are induced on the outer sphere. Are induced inside. Negative charges of magnitude 2 are induced inside the outer sphere, and no charges are on the outer sphere, since the positive charges there are neutralized by negative charges from the Earth through the Earth-work connection. So that's the arrangement. The PDV across the arrangement is equal to the potential due to the inner sphere, as you can have it here, minus electric potential due to the outer sphere, which would be this minus that, but then that one is what? Is 0, since this outer part is Earth. And therefore the PD of the whole arrangement is equivalent to the PD due to this plus, or the potential due to this plus the potential due to that. Potential due to this is this one. Then potential due to that is this one. We give it a negative because we are having negative charges there. And then you proceed and do the calculation and continue and reach here, which can also be represented as that. By doing so, you get the capacitance of two concentric spheres. By doing so, you get that. So I had told you in one of the previous lessons that you're actually going to find that the capacitance, the capacitors are of different types. Now you can see, now it means we shall have capacitors which are, we are having two spheres. We put one inside the other. Okay? That will be a capacitor. We are going to have maybe sheets, a sheet here and a sheet here on top of each other. That will be a capacitor. We are going to have different forms of capacitors, so you have to continue following these lessons, and soon we are doing a lot of calculations, and then we are understanding a lot about capacitors. Learning must continue taking place, and that one is possible at Back Science Education Consultant with me, Teacher Course specializing in physics and mathematics. We have other colleagues. You scroll in all the videos and watch the lessons. You are going to be happy and you are going to understand. Thank you for subscribing and inviting others. I pray that you may keep understanding whatever you learn from here, so that we see that our channel can help you in your academic life. Thank you very much. Thank you.